that if we happen to know the impulse response Hn to any input or to any system, then it is possible for us to find out output to any given input. So if we are given an impulse response Hn, and if we are provided any input, whatever the signal it may be, then by convolution it is possible to find out output to that particular input by convolving the signal input with the impulse response. And this is the formula, and we will look at how this formula works. But you can see that the components of the formula is that we have the signal xk, we have the signal x, we have the signal impulse response, which is h. They are being multiplied in some form, and then they are being summed up for values minus infinity to plus infinity. Okay, so we will look at how this formula works in a minute. Let's look at the definition first, that the input xn and the impulse response hn are the two signals which are processed to produce output yn as a result. And in above equation, both n and k are integers. So here you see n and here you see k. We will look at it in a minute, that what is n and what is k and why are they being used. The point to remember here is that if you know the input signal and if you know the impulse response to any system, then you can convolve these two to find out the output. Now the steps for performing the convolution are very simple. So what we do is that we have two signals, xn and hn, the impulse response and the input. We first of all start calling xn as x of k and start calling hn as h of k. The reason for changing n into k is that when we integrate or we perform summation operation along any particular independent variable, then that particular variable disappears from the equation. So if I give you an example, that for example there is a signal xt and we integrate it with respect to t, then the result after performing the limits, we do not retain the t anymore. It gets disappeared, and we get back to the numeric numbers. Here we are interested in convolving xn and hn and performing the summation operation in such a way that we get the signal yn. We do not want the n to disappear. So in order to save this n from disappearing after we perform the summation operation, the trick is to use a dummy variable k and sum the signal along k so that we can safeguard this n. So convolving xk and hk gives us y of n. So that is the reason of choosing a dummy variable. Other than that, other than this explanation, there is not much to be done. We just start calling xn and hn as xk and hk. So this is step 1. Step 2 is we fold the impulse response to about k equals to 0 and we get h of minus k. Okay. Then, and we have seen how the folding works. So we know folding. Now the step 3 is that we start shifting h of minus k to various positions, various shifts, both delay and advance. And we call the shifts as n. So we are talking about h of minus k plus n. I have written here as n minus k, but for easier understanding, you can call it h of minus k plus n. This is the third step. And the fourth step is that we keep multiplying xk, the value of xk, with h of n minus k. We will see in a minute that how it works, but this multiplication is happen is conducted at every possible instance of n till there is an overlap between xk and h of n minus k. Ideally we go till infinity, but there is no point in going towards infinity because at some point in time the x and h will stop overlapping, and this is where we stop further shifts. And the step number 5 is that once we multiply the two signals, we add all their values. You remember the big summation that allows you to sum all the multiplication points to get one value for yn. And we keep on repeating steps 3 to 5 till all possible overlaps happen between the signal xn and h of n minus k. Okay, so what we are going to do here is take an example. So we have an impulse response hn as 1, 2, 1, minus 1. We have an origin at 2, and we have the input signal xn as xn is equal to 1, 2, 3, 1, and the origin is here. So, and we have to find the output yn. This is the block diagram of the situation, that the signal xn is here, and the system is defined by the impulse response as this. Okay, so the system is defined by the impulse response, and we have to convolve the input with the impulse response to get the yn. Okay. Right, so let's look into the solution, and if you pay attention to these three rows, it will help us look at the remaining steps easily. So here is the k, which is the dummy variable for n, and we have selected some values of k as -7, -6, -5 till 7. Okay, and we have the signal xn, now called x of k, and we have placed the values as at the places where they are due, that is 1, 2, 3, and 1. And what we have done is we have folded the signal h of k to h of minus k as well, and we have placed the values as at -2 it is -1, at -1 it is 1, at 0 it is 2, and at 1 we have 1. So you can see that there is some overlap between xk and h of minus k. Now in the next steps, what we are going to do is to shift h of minus k to different positions, multiply the x of k with that signal, and add up the values. Okay, so keep your focus on what's happening in each step. Remember that the purpose of all of this is to get the output signal yn. Now if we select the shift as 0, we decide that although okay we have h of minus k and there is some overlap between xk and h of minus k, we do not apply any shift, rather we just multiply for n equals to 0. Okay, so n equals to 0 mean there is no shift in h of minus k. The next step is to multiply x of k with h of minus k. So 0 multiplied by -1 plus 0 multiplied by 1 plus 1 multiplied by 2 plus 2 multiplied by 1 plus 3 multiplied by 0 plus 1 multiplied by 0. Okay, so essentially what we are saying here is we are multiplying 1 with 2 and 2 plus 1, so which is represented here 1 times 2 plus 2 times 1, and the sum is 4. So we get y of 0 as 4. Okay, now let's look at the next step. We are going to move n as 1. So xk remain wherever it is, and with this 1 we have moved h of minus k by 1 unit. So h of minus k plus 1, we have seen that when we do h of minus k plus 1, the signal is delayed by 1 unit and then folded. So previously h of minus k was here, and h of 1 minus k or minus k plus 1 will be moved to these positions. So now once we have these two signals in place, then we can multiply the values which are overlapping. So 1 times 1, keep an eye on this line, 1 times 1 plus 2 times 2 plus 3 times 1 gives us 8. So for n equals to 1, we now have the value for y as 8. Similarly, when we move n equals to 2, then there is another shift in h of minus k to h of minus k plus 2, and now there are all the values are overlapping. So we have 1 multiplied by, again keep an eye at this box. So we have 1 multiplied by minus 1 plus 2 multiplied by 1 plus 3 multiplied by 2 plus 1 multiplied by 1, and that gives us again the value as 8. Minus 1 plus 2 plus 6 plus 1, we get 8. And similarly the operation continues, and this is for n equals to 3, for n equals to 4, for n equals to 5. You can see for n equals to 5 there is only one last overlap, so 1 into minus 1 is minus 1. And when we move to 6, n equals to 6, there is no overlap, so there is no point moving n equals to n to further positive values. Now let's look at n negative values, because I can see that there are certain overlaps on the negative side of n as well. So n of minus 1, h of minus k goes to h of minus k minus 1. So there is single overlap, 1 times 1 is 1. And for n equals to minus 2, again there is no overlap, right? So the signal values become, the output values becomes 4, 8, 8, 3, minus 2, minus 1, and towards the negative side it is 1. So if you arrange these things properly, then this is the final result. We get 1, 4, 8, 8, 3, minus 2, minus 1, and 0. And the point to remember is that if the length of signal xn is L and the length of signal hn is m, then the length of the convolution sum will be L plus m minus 1. So there were 4 samples for the signal x and impulse response. So 4 plus 4 is 8, minus 1 7. So there must be 7 values. So 1, 2, 3, 4, 5, 6, 7. So 7 values are here. So that's how the convolution is computed. This is another way of computing convolution. We can discuss it in the live class. It's not very difficult. You can simply look at it for a minute and understand how these are calculated. And this is a link I would recommend all of you to go and try to see how convolution sum impacts the outputs. So we looked at some of the time domain manipulations of signal, including shifting and folding, and we also looked at the convolution sum in detail. And these are the reading and practice sections from your book, section 2.1.3 and section 2.3.3 and 2.3.4. So that's it. Thank you very much.